Okay, so plan for this week's gonna go something like this. Okay, today we're gonna go over, more in-depth vector-related Newton's second law questions. So there'll be a bit more tail to head, a bit more trigonometry kind of stuff with these ones. Tomorrow we're gonna do our lab. Okay, so we'll have the tracks and the pulleys and the carts and masses, and we'll do our lab tomorrow. Wednesday, we'll probably kind of clean up the rest of Newton's second law and talk a bit about the force of friction. Thursday, if we're looking fairly good in terms of where we are, I will probably give you the unit assignment for Newton's second law and give you the class to work on that. And then Friday, you'll obviously have your quiz on Newton's second law. Okay, so that's kind of the plan for the week here. The other thing I need to let you know about is I do have to cancel tomorrow's lunchtime help session. I will be here for scheduled help, so if you want to pop in tomorrow at scheduled help, I will be here for that. But something came up and I have to pop out over lunch. So if you're looking to get help tomorrow at lunch, I have to cancel that one, pop in at scheduled help instead, and I can help you out then. All right? Okay, I want you guys to copy that one down. Okay, very, very vector-ish. All right, so copy that one down, get a free body diagram and a vector diagram drawn, and then stop. Okay, then we'll kind of look at what that's supposed to look like, and I'll let you finish it up after that. Okay, so got to have our two diagrams here. Our free body diagram is going to be kind of like our givens. Okay, so we'll have our 50 kilogram box. Okay, and it's being pulled along a level frictionless floor by two forces. So basically, this diagram is me looking down on the mass. Okay, so one of them is 35 degrees north of east and is 150 newtons. Okay, so here's east. Okay, 35 degrees would probably look something like that. Okay, so 35, 150 newtons. Okay, and then force 2 is directed 10 degrees south of east, and it's only 115 newtons. So 10 degrees south of east would probably look more like that, and it's only 115 newtons. Okay, doesn't mention, it says it's frictionless, so I know that those are now then the only two forces that matter. Are gravity and normal force there? They are, but it's not moving vertically, right? It's on a horizontal frictionless surface. It's not coming off of it, okay? So I don't have to worry about those. So the next thing I'd want to do then is draw my vector diagram. So, okay, that would be my 150 newtons. This would be my 35 degrees north of east, x and y. And then south of east, 10 degrees. 115 newtons, x, y, and then my resultants. You can draw the resultants triangle either way. This is just the way I'm drawing it. Okay, what does my resultant represent?
The actual journey of the box, like the direction of the force, right?
Yes, what do we call that? F.
Oh, F net.
F net, it's the vector sum, right, of all of those two forces. Okay, so when I'm doing one of these, okay, F net is going to be my resultants. Okay, in the last unit it was usually displacement. In this unit it's going to be net force. And okay, this is going to be the direction that that box is going to go. The acceleration will also be in that direction. All right, I'll give you a little bit of time to get back ahead of me here, okay, and then we'll walk through the rest. So we got to find all of our x and y components here. So we'll start out with the first triangle, the red one. Okay, so red x is the adjacent side, so that'll be the cos of 35 times 150 newtons. Okay, so we're looking at 122.87 newtons east. All right, y is going to be the sine of 35. 150. Okay, so that side will be 86.04 newtons, that'll be north. Okay, and then for the green triangle, okay, x is also adjacent in that triangle, so cos of 10 times 115 newtons. Okay, is 113.25 newtons, and that is also east. Okay, and then green y, sine of 10 degrees times 115 newtons. So 19.97 newtons south. Okay, so now I've got all my x's, all my y's. Okay, to get purple x and purple y, I've got to put those together. All right, purple x will be red x plus green x. They're both east, so I don't have to make either one of them negative. I just need to put them together. Okay, so that was green x. Okay, that was red x. And we are looking at 236.13 newtons, and that is east. But for purple y, I've got one that's north and one that's south. Okay, so I do need to make one of them negative. So I'm going to go up to the bigger one here and make it positive, and then just subtract the smaller one. All right, so our purple y is going to be 66.07 newtons north. Okay, still ended up being positive. What do I do now? Pythagorean theorem. I heard somebody whisper. Okay, Pythagorean theorem is the next thing, so that'll get me the magnitude of my net force. All right, so F net will be the square root of the 236 with all the decimals squared plus the 66 with all the decimals squared. Okay, just like any other vector addition question, we've done so many of these. All right, so our net force is 245.19 newtons. Okay, and then we need the direction as well. Tan to the minus 1. For me, the opposite side was y, so that's the 66 over adjacent to 236. Okay, so I'm getting 15.63 degrees north of east. Okay, what did the question want? It wanted acceleration. All right, so just like any other question we've done, I just did the vector sum of all forces part, and now I need to do the F equals m times a part. Okay, so acceleration equals F net divided by mass. So that'll be our 245 newtons, okay, with all the decimals, divided by our mass, which was 50 kilograms. All right, so we should get 4.9. We only have two significant digits here. Okay, 4.9 meters per second squared at 16 degrees. 16 degrees north of east. Okay? So other than at the end of that, you had to do F net equals m times a, was it any different than any other vector addition question you've done for me? Okay? That's the thing about this unit. It's going to use the skills you already have. Right? It's just going to use them in a different way. But it doesn't change that you use them, you do them the same way. Okay? I still draw them tail to head, find all the x's and y's. That part doesn't change. Okay? Any questions on that one? Okay, like that's one I would totally put on like a quiz. Okay, for sure on a quiz, maybe even on a test. Okay, makes you do some vector addition and some Newton's second law. Okay, we did that one. And we did that one. We didn't end up doing that one, did we? Maybe we'll do that one eventually. Okay. In the digital workbook, there is a or in the workbook if you printed it, there's a whole page that just force is a vector quantity problems. All right, so there are some on there that I want you to do, okay, right now to try. So I'm just going to bring it up here, and then I'll write the numbers on the board that I want you to do. Okay, so it's right after the inclined planes worksheet that we were working on last week. Okay, so I would like you guys to be working on 1, 4, 5, 7, 9 for now. Okay, so 1, 4, 5, 7, and 9 for now. Yes. Okay, I'll scroll it up in a few minutes, but okay, you guys can get started on those. Okay, so in number 1, we've got the car being pulled. The car is 1,500 kilograms, and we're told that the force acting on it is acting 45 degrees above the horizontal. Okay, so 45 degrees with the road, and has 2,000 newtons, okay, worth of tension in it. And we know that friction is opposing with a force of 500 newtons. Where do I draw the friction? Straight back? Yeah. Because which direction is the car going? Straight forwards, right? So friction always acts straight backwards. So this, or always opposes the motion. Okay? Yes, we might have this force here, but this part of it right here is offsetting what? Partly gravity, okay, partly normal force. It's, you know, it's got normal force and this are both acting up, and they're offsetting gravity. The car's not coming off the ground, okay, or it's not accelerating vertically, right? It's just moving along horizontally. So the only force I'm really concerned about is the horizontal component of that 2,000 newtons, right? All the other ones, from the context of the question, are irrelevant. Okay, because the car isn't moving vertically. So F horizontal, okay, is going to be the cos of 45, or the sine of 45, so it'll be the same thing, okay, times 2,000 newtons. Okay, so 1,414.21. That's my force forward. Okay, since the car is only going forward, I only have to worry about forces going forward and backward. That's that force and 500 newtons worth of friction. So can I do vector sum of all forces now? Pretty sure I can. Okay, the forces that I'm concerned with, okay, are the horizontal component of the tension plus the force of friction, and I have both of those. So 1,414.21 plus negative 500, right, should give me 914.21 newtons. Okay, forward. All right, so there's my vector sum of all forces. Now, does it seem like there should be more to it than that? Like sometimes people read that and they're like doing all of this trade, they're putting gravity in there. Gravity's there for sure, but gravity acts vertically downward and the car isn't moving vertically. So if it's not moving vertically, What's the net force vertically? Okay, Max just gave me the 0 sign. Okay, so yeah, 0, right? The net force vertically is 0. That means that we're only worried about horizontal forces here. I can then go acceleration is F net divided by mass, okay, 914.20, okay, divided by the 1,500 kilograms, okay, and I should get my positive 0.609 or 0.609 meters per second squared forwards. Okay, everybody all right with that? The vector ones, again, what's tricky with the vector ones are not you having to put vectors together. I know you can do that. The vector ones, the part that's tricky is figuring out what forces actually matter. Okay, it's the context of the vector questions that's tricky. All right, I'll put those back up and you guys can keep going. What are the key words in number 4?
Constant speed.
Constant speed. What does that mean for the net force? Constant speed, net force is? 0. Okay, so here's the fish. He's very unhappy because he has a hook in his face. Okay, and we know that the line is angled at 45 degrees. We know that water resistance is opposing the motion with 80 newtons. Now it does say it's moving horizontally, so that means I can draw the 80 newtons straight back. What they want is the tension in the line. So I've already got the acceleration, it's 0, right? And I know the vector sum of all the forces is 0. So if the vector sum of all the forces is 0, how big is this side of the line's tension? If it's moving at a constant speed and I got 80 newtons backwards, how many newtons forwards do I have? Yvette, how many newtons forward? Oh, no, the sum would be 0, yes. So how many forward? If I got 80 back and the sum is 0, I'd have how many forward? 80, yeah. Okay. There has to be the same amount forward because if I add forward and backward together and get 0, they got to be equal. Okay. So there's 80 newtons worth of tension forwards. I want the tension in the hypotenuse. Well, I have the angle. Okay. It's just a matter of doing a little bit of trig. This is a question that has very little math in it. Right? I have to do one trigonometry calculation to answer this question. Okay? And that's it, because it gave me those words, constant velocity, which always makes my life a little bit easier. So if I want to get the hypotenuse there, okay, all I'm going to do is go the cos of 45 equals 80, okay, over the tension in the line. So if I want to get the tension in the line, it'll be 80 divided by the cos of 45. Okay, when I do that, I should get 113 newtons, 45 degrees from the horizontal. It is tension, so I don't have to put the 45 or the 45 degrees. I can just write 113 newtons, and that would be good. Okay, so tricky question. Okay, not a lot of work to do, but tricky. Right? There's a lot of intuitive stuff that has to go on there.
Is friction always going to be on the horizontal axis?
It's always going to directly oppose the direction the object's going.
Wasn't it moving that way?
Nope, it says it's moving horizontally.
Oh, just straight up. Oh, yeah, I see.
Right? If it says that, then that's how I know to put it straight back.
Okay.
Yeah, if I don't say that, then this question becomes, yeah, a bit more tricky.
Okay.
Okay, all right, keep going. I'll put the sheet back up. Okay, if the rock is sliding along the ice, okay, nobody's pushing it, are they? Right? It doesn't say that anywhere. It just says that it's sliding, and it tells us that its acceleration is negative, which means it's sliding and slowing down. All right, so if I'm diagramming this, I've got the curling rock, right, which is 12 kilograms. Okay, I've got normal force, I've got gravity, but they're balanced because it says it's sliding along a sheet of ice. It's not moving vertically. So the other force involved here would be the force of friction, agreed? And that's the force they want me to find. Well, if these two forces cancel each other out, is friction the only force we're concerned with then? Is it then by default the net force? That happens a lot. That's the purpose of this question. Okay? It happens a lot that if you've got something that's sliding to a stop, okay, like you slam on the brakes and your car slides to a stop, friction is the net force in those situations, assuming you're on a level surface. Okay? So friction becomes the net force because it's the only force. So since they told you the acceleration, and they told you the mass of the rock, okay, you can get the force of friction because it's the net force. Okay? All you have to do is go mass times acceleration, and you've got the force of friction because it's the force that's causing the rock to slow down. That force and only that force. Okay? Everybody all right with that? Again, it's another one of those, like this would barely be a 3-mark question on a quiz. You had to do one calculation to get it, right? But there was thought that went into it. Now, something else I want to illustrate with this example here is something we're going to talk about later this week. Okay? And it's how the force of friction works. Okay? We said we had the force of friction back here. Okay? What kind of things can affect how much friction there is?
Mass.
Yeah. How big something is can affect how much friction there is because gravity pulls more on bigger masses. So actually the weight, but also the mass, okay, of an object. If I had a 12 kilogram object and a 50 kilogram object, there would be more friction on the 50 kilogram object because of these two forces. The normal force and the force of gravity. Okay? On your formula sheet, you have this formula. It says the force of friction is mu times the normal force. Okay? So what that means is, in this situation, if I have a bigger mass, gravity would be bigger, and thus the normal force would be bigger. Okay? And that would cause friction to get bigger. Mu describes the two surfaces that are interacting, right? For a curling rock, the rock and the ice have a very low mu. Okay? We call that the coefficient of friction. Those two surfaces slide past each other very easily. If that was like sandpaper and asphalt, that would be a much higher number. It would be much harder to get that thing to slide along because mu would be a much bigger number in that situation. Does that sort of make sense? So those are the two things that can affect how much friction there is. In this situation, mu is probably a pretty small number. Okay. All right. How are we doing on number 9? Okay, how many people have done 9? All right, I'm going to give you a few more minutes to finish up 9 because I definitely want to go over that one. That's our lab tomorrow. Okay, so it's pretty important. Okay, so with number 9 here, we've got the table that's got the mass sitting on it. Okay, that mass is 4.5 kilograms. Okay, and it's attached over that pulley, okay, to the 6 kilogram mass. Okay, and we know that friction is opposing with 4 newtons worth of force. So I'm just going to draw that back here, okay, because that's opposing the motion. All right, what's this force? Gravity, yeah, the force of gravity. All right, so that's going to be m times g, 6 times 9.81, should be 58.86 newtons. Okay, everybody all right with that? All right, so those are the only two forces acting in this situation. Okay, so what I should have then, okay, is that my net force would be the vector sum of those two forces. All right, so can I simplify this diagram then at this point? Because this is a system, right? There's 10 kilograms worth of mass being accelerated by the net force. So I'm just going to simplify this to 10 kilograms with 4.0 newtons worth of force acting backwards, 58.86 58.86 newtons acting forwards, even though it's technically not forwards. Okay? And so we should end up with an F net then, 58.86 minus 4, so 54.86, okay, newtons. Right? Everybody okay with that? I don't think that answer is right. Doesn't seem big enough. Okay, did I have the masses wrong? 4.5, that's why it didn't seem, sorry. This is 4.5 kilograms, so this should be 10.5 kilograms. Okay, that's 4 newtons, 10.5 kilograms. See, you guys gotta catch me when I make mistakes. Okay, so now I've got my net force, 54.86 newtons. Okay, now I can calculate my acceleration. F net, okay, divided by m, so that'll be 54.86 divided by 10.5 kilograms. Okay, that should give me my 5.2. Now it did ask, what's the acceleration of mass 1? So then I can give a direction on that. Okay, everyone all right with that? So this is going to be tomorrow's lab. So I want you to kind of picture this situation. Okay, we'll have those tracks. You're going to have those tracks on top of the desks tomorrow because they have to be elevated, right? Otherwise, how do you have the masses fall? If you put it on the floor, it really doesn't work. Okay, so you're going to have those tracks on the desk. You're going to have the cart on the track, okay, and we're going to drop the masses. So gravity is obviously going to be the driving force in this situation. I want you to think about, in that situation, what other forces may or may not be present. Okay, we are, after all, doing this experiment in the real world. Okay, some things to think about for possible sources of error for tomorrow. Okay, when we're setting that up, or things to check for and make sure that they're right. Okay, when you're setting that up tomorrow. Okay. All right, I'm going to put up that inclined plane with the 3 masses and the 2 pulleys now. Okay, and I want you guys to give that one a try because you're ready now. Okay, totally ready for that. Where did it go? There. Okay. So we want the acceleration of the 5 kilogram box. It's a 20-degree incline. Okay, you got an 8 kilogram box hanging over the top pulley, a 10 kilogram box hanging over the bottom pulley. Okay, they can both be acted on by gravity. Okay. Think about what other forces are going to be present in there, maybe some that act on the 5 kilogram mass. Okay. And we can assume that this system is frictionless. Okay, we're going to assume that for the purpose of this question, because otherwise it gets even more crazy. Okay. Okay, in case you're just really stuck getting it going, all right, let's just kind of look at what forces might be involved here. All right, so is there a force acting on the 8 kilogram mass? Which one? Gravity, right. Okay, so there's going to be a force of gravity pulling the 8 kilogram mass this way. That'll be 78.48 newtons. Okay, 8 times 9.81. Is gravity also acting on the 10 kilogram mass? Okay, so we got 98.1 newtons worth of gravitational force here. What other force is acting in here that we have to be concerned with? Okay, I've got those 2 gravities. Where's the other gravity?
It's acting on the 5 kilogram box straight down, and it goes down to be the x-axis of that triangle there.
Right. Okay, I'm going to have this force, F parallel. Right, I've got that force is still there. Gravity wants to try and pull that thing straight down. The ramp semi-prevents it. That's where F parallel comes from. Okay, so we got that 20-degree angle in there. Okay, so we got to go 5 times 9.81, so that'll be 49.05. Okay, you're looking for F parallel. Okay, I'll give you a few more minutes on that one. Okay, so the tricky part with this is obviously not calculating the individual forces. Okay, it's kind of figuring out how they go together. So we've calculated all the forces of gravity. We still need to calculate F parallel. It's the opposite side. So we'll go sine of 20 times 49.05. So F parallel is 16.78 newtons. I figured out all the forces that are involved in the movement of this system. All right, now I want to simplify the system, as I want to as often as I can with any system. So what I have is 23.0 kilograms worth of mass, okay? And now I can make all these forces forward and backward, all right? Obviously, I'm going to have my 78.48 newtons that way, okay? That's gravity on the 8 kilogram mass. The other two forces act together. Because of this pulley, this force is actually pulling the system this way. All right, so I can actually say I've got 16.78 newtons and 98.1 newtons, both acting that direction. Okay, because of the pulleys, they essentially pull in the same direction. That's the tricky part of that question. All right, the second tricky part was remembering to make the total mass of the system 23. All right, so now, okay, I can get my F net. Okay, my vector sum of all forces. So I'll have 98.1 plus that number, okay, minus the 78.48 because it was opposite. All right, so my net force then is 36.396 newtons. All right, and then I can calculate the acceleration, F net divided by mass, so 36.396. divided by the total mass of the system, 23 kilograms. All right, so the acceleration of this system is 1.6. We only have two significant digits there, so 1.6 meters per second squared. Now, the question wants the acceleration of the 5 kilogram mass. So 1.6 meters per second squared, down the ramp, exactly. All right, was that as hard as you thought it would be when you started it? Right, and that's the key here, guys, is it's easy to get intimidated visually by a Newton's second law question, but always remember, the individual parts are never going to be all that difficult. And it's always going to come down to vector sum of all forces, m times a. You're going to get sick of me hearing that, but it needs to be the reassuring part, okay, of all Newton's second law problems. That looks very intimidating, okay, when you start it. But then when you start to realize, gee, there's only like 3 forces here that really matter. I can calculate those. This isn't so bad.
I'm a bit confused because I don't understand how the 10 kilogram block can cause the whole system to have, like, wouldn't it, when calculating the acceleration of the 5 kilogram block, wouldn't you only use the forces that are like resisting? Kind of like, so I did 13 kilograms because I thought the 10 kilogram only caused acceleration.
No, all of that mass has to go together. The whole system is accelerating together. All the parts are attached. Okay, so in any system, you got attached masses, it's always the full mass. Okay, I wouldn't have that force if it wasn't for that mass. That mass has to go along with it. Yes, it's providing the accelerating force, you're 100% right on that, but it's also part of the mass that has to be moved, right? This force is resisting it, so I've got to put it in there.
I see.
Okay, yeah, that's a good question. Okay, so tomorrow lab, okay, come ready to do the lab. You'll need that SparkView app, or at least one member of your group is going to need the SparkView app on their phone to record the data from the carts. The actual lab part of it, like getting the data, shouldn't take us very long. We're just doing a couple of trials, moving some masses around and firing away. And then you'll have the rest of the class to work on the lab report, so hopefully you'll get a good chunk of it done in class. Okay, please remember tomorrow, no help at lunch, but there will be scheduled help, so if you need help, come in then. Okay, sorry that I have to do that, just sometimes stuff comes up. Okay, but I will be here at my other help for the rest of the week. Okay, we'll quit a little early there, guys. Good work today.